Okay, this is Astronomy 1, Chapter 2, Observing the Sky, the Birth of Astronomy. Okay, and so this chapter will focus on three things. The sky above, still quite general. We won't be very specific. Um, the ancient astronomy, some of it, and a breeze from a breeze that joins ancient astronomy to the modern astronomy. Learning objectives for this course. When we're through with this course, you should be able to define some of the terms that we use in this chapter and the rest of the course. What celestial sphere is, what zenith is, what the there are terms that astronomers use to describe the sky. So you should be able to explain most of those terms. Also, you should be able to describe the path of the sun, moon in the sky, in the day sky and night sky, including the motion of the stars and planets as they appear to us on the earth, and then understand the term constellation. Here is the night sky as it is seen from Arlington, Texas. No, I'm kidding. Uh, Sadly, we are robbed by our own invention of electric light. We have street lights, building lights, we have lights everywhere, car lights, headlights, and we call the light pollution that has destroyed our night sky. We barely see any stars in the sky these days. Okay, you really have to go far out in the countryside where there are no lights. My favorite place is Big Bend National Park. It is quite a drive, 8 hours, almost 8 hours from Arlington to Big Bend National Park, which has very less lights, and so you are there at night. You know, you do get to see the band of Milky Way rise and set. So, for example, here this is the band of Milky Way, and here there are all the stars, even galactic galaxies, the small galaxies, as you see here in the left corner, the large Magellanic Cloud and the small Magellanic Cloud. And this is, as viewed from the southern hemisphere, Atacama Desert in Chile. This desert here in Chile, it has not rained there for many years, and that's good for observation, astronomy, research, because as there are no clouds, the night sky is always clear, dark, and it is quite far from the civilization, and so you'll that desert here, Atacama, houses many telescopes like this one here, and so so this is night sky. Okay, we I don't think there's anyone who doesn't enjoy a night sky. Watching stars. Watching the shooting stars, the falling meteoroids, and whatnot. Um, Plus, it's also night sky is romantic. There are many poems, written uh, based on the night sky, based on the Milky Way, and so on. So, despite so all that fun part, enjoyment, relaxing poems, even maybe novels, there is science to it. Okay, and it started with the ancient civilization, ancient people, around the world. They noticed something, that at night these stars, these galaxies, these clouds, The milk is spilled here in the sky, hence the name Milky Way galaxy. The ancient thought, it's the gods who spilled milk, and hence called the Milky Way, the path of the milk. You know, every object here, would rise and set. They would all rise in certain direction. Now we call that direction east, like all the sun and moon rise. Um, in the east and sets in the west, and there the sun visible in the daytime, in the nighttime, all the stars and moon and the clouds here, even the galaxies, they rise and set, and the old civilization, some of them they worshipped. Uh, Many religions are formed. Uh, uh, or the religions they explain these things from their religious view and whatnot. But again, later on they started to observe in a scientific way and explain what all this is about, why all these stars rise at certain time and sets at certain time, and even the path of that rise and set, the path would differ, depending on where you are on the earth. And so to explain all that motion, the modern astronomy, took over, and that's when we started to organize it. And so we gave certain terms, and now we'll define some of these terms, like for example, you are standing on a very large empty field at night. What do you see? You see a night sky, a dome around you. There's a horizon that where that dome, the um, virtual dome that covers you, and then it ends at that ending point. And so that point where the dome meets the earth, we call that the horizon point. And we can define a point that wherever you are standing, a point directly above the head, that point as the zenith. Okay, so here are two important terms to remember for the rest of the chapter and for the rest of the course. And so now let's expand this a little bit. Okay, this is a very simple version. So now we know what horizon is, what zenith is, what dome is, and so to take it one step further, that dome, is actually a imaginary sphere. We call that a celestial sphere, which is kind of projected outward from the earth. So we see, and whatever stars that we see out in the sky, or it's as if all those stars are embedded in this imaginary sphere, which is basically a sky, the dome of the sky. It's just a great sphere, and that sphere turns, meaning that sphere rises and sets. It rises in the east and rises in the west. And so it's like the whole that dome is moving. But now we know it's the Earth's rotation that creates that, that phenomena. But, ancient time, or the beginning, when we're trying to define every phenomena in the sky that we see, it did seem like there's a whole celestial sphere above us. So this is our horizon. I'm standing somewhere here in the equator. Okay, this is Earth. This is the equator here, dark circle. I'm standing at the equator, and this is the North Pole, South Pole. So that I am in the so that I'm standing in the equator, and I want to be perpendicular to the horizon. So my zenith is above my head. So this whole Earth is kind of tilted. for reference. Okay, it's not like this in reality. Usually the North Pole is up, and the equator is horizontal. But again, that's just for the purpose of definition. So I'm standing here on the equator. My zenith is directly above my head. That's my zenith point. And this imaginary sphere is called the celestial sphere. It's like when I'm watching a stars, these stars are like embedded within this sphere. That's what it seems like, the apparent position of the stars in the sky. Okay, that's the celestial sphere. And the North Pole, this is the North Pole, this is the South Pole of the Earth, and we can project these poles outward until those, projection reaches the celestial sphere itself, and that's showing the rotation of the Earth. And the projected North Pole is called the North Celestial Pole, and down here would be the South Celestial Pole. And we can also project the Earth's equator. So this is the Earth's actual equator on the surface of the Earth, and if we can expand it out until it reaches that celestial sphere, that would be the celestial equator. So that's the Earth's equator expanded out, that celestial equator, and the horizon as I'm standing here, this whole celestial sphere, meets at the Earth's horizon here, and that's the horizon as we defined earlier. So here we now know what celestial sphere is: an imaginary sphere around the Earth, where objects like stars seem to be fixed in that sphere, and that sphere seems to rotate, rise and set. Along with that, all the stars rise and set. And the celestial poles are the projection of the North Pole and South Pole. And the celestial equator is the projection of the Earth's equator out here. And as that dome seems to rotate, or as the dome rotates, it rotates. Again, that's the effect of the Earth's rotation, but we can, for now, call that dome rotating. And so this is where the celestial sphere is, and all these stars, the Milky Way band, is embedded in that celestial sphere. And this is a time-lapse video. Of course, we don't see this fast. It takes 12 hours for the whole rotation to take, or 24 hours to come around again. This is a time-lapse video, and so it seems here that the sky, is rotating. The whole celestial sphere is rotating, and most importantly, here is another fact, that the apparent motion of the celestial sphere depends on our latitude. So what that means is how these stars rotate. Their motion depends on where we stand on the Earth's surface. So if we are standing on the North Pole, the stars would rotate when we see, the way they rotate would be form a certain shape, versus when we stand at the equator, they would be different. So for example, here, this is again at the South Celestial Pole, sphere around the South Celestial Pole, standing at the Southern Pole. As the Earth, as that celestial sphere rotates, all the stars rotate around. And this is again is a long exposure picture here. This, I assume, should be about 1 or 2 hours, because the star trail that I see, if I take a snapshot, then there would just be stars at one point. But if I that's what the long exposure means. If I open my camera shutter for 1 hour, 2 hours or so, it's during that time, the stars have moved. the stars have rotated, and so that's what this one single line is. That, or this one here, the stars have moved this much distance in, let's say, 1 hour, if my camera exposure time is 1 hour. The phones that we have, when you take a picture, it's about, microsecond, millisecond time frame. For that long, the shutter opens and closes. Um, but to take, star trail pictures like this, of course, we need to open the shutter for longer hours. And again, this is as seen from the um, South Pole. And so to continue that, how star circles at different latitude. So what is latitude? First of all, it's the Earth is divided here into different angles or different latitudes. It's 0 degrees at the equator, and it goes from 1 to 3 up to 90 degrees until it reaches the North Pole. So, the let's say this specific country here, some looks like African country, you can tell what latitude that place is. So the equator, which is the largest circumference of this sphere, is at 0 degrees, and if you go up towards the North Pole, it's rise in the latitude. So these are northern latitudes. Some book you may see these as negative going towards the South Pole, or these are southern latitudes, go down, and the angle changes going from 0 to 90 degrees. And also they are divided longitudinally. These are longitudinal latitudes here. We'll come to this later. But what I'm trying to get is, how the sky looks, how the stars rise and set differs depending on what latitude you are standing on is. Okay. For example, you're standing at the 90-degree latitude, which is the North Pole here. Okay, so I'm standing here, and this red one is again my horizon. Horizon and the zenith. This is my zenith line here, and also that's the north celestial pole. When I'm standing at the North Pole and I look at the sky, the stars there don't rise and set. They simply go in a circular path, because Earth is rotating here from west to east. Earth rotates from west to east. That's why all other objects rise at east and sets at west. It's just opposite. When one move, it's only one thing that's moving. It's the Earth that is rotating. Sun is fixed here. So when Earth rotates from west to east, the sun appears to rise in the east and set in the west. So Earth is rotating in this direction. So that causes, all the stars that are embedded in the celestial sphere, these stars rise in the east and set in the west. So the star trail looks completely circular when you're at the North Pole. And B, when I'm standing at the equator now, the equator is out here, so I can rotate this Earth. It just, again, just for reference. So when I'm standing at the equator, then the celestial pole here, the north celestial pole, is this one. And so now when I see the stars, same stars here, rising and setting, it's now everything forms a half circle. When I am at the equator, the stars would rise here at the horizon and go around and set. After a certain time, they would set in the west. Same thing here. Their circumference length would be different, because the circles have different diameters, and so every star should rise and set, other than the one at the center. I'll come to that. That appeared to not move because it's exactly at the celestial pole. In this case, it's the north celestial pole, and that's the case for the equator. And when for intermediate latitude, I can be, I don't have to be at the equator or the North Pole. It can be some angle above the equator, and in that case, I would see a intermediate trail of the stars. Like some stars would rise and set, but anything that are very close, to the central, close to the north celestial pole, would only go in a circular path. And I can reverse this and look towards the south celestial pole, and it repeats itself. Okay, so more on uh, the appearance of the stars as they rise and set, or more on the star trails as viewed from different latitude and different latitude of the Earth. And so again, this is the Earth with different latitudes shown here, and so it forms this zone called circumpolar zone. What that means is when we are at some intermediate latitude, for example, 38 degrees north, so you can measure 0 degrees, 38 degrees somewhere here, 38 degrees north. If we are at that point, as shown in this example back here, it appears that the sum of these stars that simply go in a circular path, they don't rise and set. So again, if we are there the whole time, whole 24 hours time, standing here, we would see a complete circular path set by the star. Again, not all stars, but those stars that are in the circumpolar zone. And there are others out farther stars that do maybe rise or maybe set for a few hours and again rise again. Yeah, and this is the same effect in Alaska during the summertime. The daylight hours are so long, almost 20-21 hours. So it's even the sun. It rises here in Texas. It sets at maybe 9 p.m., 8:30, 9 p.m. It sets in the summer, and it rises back again in the morning. But that nighttime hours is longer compared to when you're in Alaska. You are in the more higher latitude, and so there, sun sets maybe for a few hours, like just grazes down through the horizon and comes back again. And you go even move further up towards the Arctic. There, the sun never sets in the during the summer. It goes, just grazes through the horizon and again comes back up and forms these type of circular loops. But again, when the tilt is on the other side, or during the winter, the tilt is on the other side, and that sun actually never comes out of the horizon for another 6 months or so. So those details, those geometry will come and see later when we study the day and nights sunrise and sunset in more detail. But for now, I just wanted to understand what this circumpolar zone is. And for observers in the continental United States, there are these star groups. We'll study about these star groups later. The Big Dipper, Little Dipper, Cassiopeia. These star groups for us here in the northern hemisphere or in the United States, these star groups lie within this circumpolar zone, and these star groups don't appear to rise or set. They form this; they're always visible. And one more thing about the when I'm here, the circumpolar zone. I've been showing that celestial pole here, especially the north celestial pole. As Earth rotates about, and that's like a rotation axis of the Earth. And along this north celestial pole lies one very specific star, the pole star, the northern star. Okay. That, the Earth rotates about that axis, and that axis points along the line of sight of the pole star. And for that reason, all stars, every astronomical bodies that's seen from the Earth seem to rise and set, and they move their position. But that northern star, as it lies, straight along the north celestial pole, the north star do not move. And for that reason, the ancient travelers, adventure people, they they take that north star as a guiding star. It since star don't move, you can always take that as your reference point. If something moves, you're saying, okay, I'm heading that way, and in real life, you may point out to a large tree or a large building, and someone says, okay, you go towards that building. You walk toward the building and you get there, or a tree or a mountain, you get there. But if those things are moving, right? Someone says, okay, go walk towards that tree, and you start walking, and after some time, that tree has moved somewhere else. You're not, you don't know where you're going. So any other moving stars could not act as a good reference point versus the North Pole, that never sets or rises, and it's always fixed there. And here is a very very nice. It's like an art. Okay, this is a real image taken by Robert Schwartz from the South Pole, one of the telescope in South Pole. You can still see some parts of the telescope here around it. But what this is pointing at the south celestial pole. That's where it is pointing. And as you said earlier, stars do not, dip in the horizon when you are at the North Pole. Even in Texas, they rise in the evening, they set in the morning. Right? You see rising and setting from east to west. But when you are at the North Pole, there is no rise and set. When you look up, the stars seem to just go in a circular path. I mean, this is taken for a whole 24 hour. So the camera was basically was looking at the motion of the star, taking picture or a long exposure picture, which is like a video. Take a rich snapshot. You can take and stack them together. Maybe take one per second and stack them for 24 hours. That's a lot of stacks, and you'd get these type of circular motion of the star, or also called the star trails. And again, they form these complete circles. And these type of complete circles are only viewable, observable from 2 points on Earth, two celestial poles, the North Pole, looking towards the celestial pole, but standing at the North Pole and the South Pole. Any other latitudes, this view, the star view, the night sky view changes. And another beautiful aspect of this image is this green cloud here. This green cloud are the southern lights, similar to northern lights, aurora borealis. They're called the Australis borealis or Australis, aurora australis. These, when the plasma from the sun, when they enters the Earth's atmosphere, the magnetic field of the Earth, guides the charged particle from the sun towards the pole of the Earth. Because the magnetic field of the Earth, they originate um, between the North Pole and the South Pole. So the magnetic field forms its own dome, a protective shield, and when the charged particles enter the atmosphere, they hit these magnetic field lines, a circular dome-like structure, and the charged particles from the sun, they follow this magnetic field, and some of them go towards the North Pole, and some of them go towards the South Pole. And when the charged particle hits the atmosphere, the atoms and molecules that are on the surface of the Earth, the charged particle ionizes those atoms and molecules, and during that ionization process produces these lights of different colors. If it's oxygen, it's one color; nitrogen, it's another color. So you see here, it's a specific. I believe this is nitrogen because we have so much abundance of nitrogen in our atmosphere. If it's any other element, then we see different colors, and we do see multiple colors as auroras in the northern hemisphere, in the towards the North Pole and the South Pole. And so, what happens at the daytime, right? At the night, we see it is there are so many stars that we see millions, billions of the stars, and we see sometimes meteorites falling, and even asteroids falling. Hopefully, we don't see asteroids that often because those can be deadly. They have wiped out civilization, the life, not civilization, other forms of life, so many times. We call the mass extinction. I think there have been 4 or 5 mass extinctions on the Earth due to asteroid impact. And the night sky. It's I would say it's more romantic than the day sky. In day we only see one star, the sun, rising and setting. Mornings or evenings are fun because it's less intensity and the sky gets prettier. It's nice. It's fun to see sunset above the horizon of mountains or lakes or oceans and such. But during the daytime, it just, especially during the hot Texas summer, sun or daytime is not so fun. But with perspective of astronomy, it carries equal importance. What happens during the daytime. So we only see stars in the nighttime because there is no sun. So sunlight, the intensity is so high, or it's just so bright during the day that all the lights, all the stars that are in the sky, or all the lights that have reached to us from those stars, they are simply obscured by the much brighter light from the sun. So we don't see stars rise and set, but in reality they do. And there's like one time when we actually get to see the stars during the daytime, and that's during the solar eclipse, the total solar eclipse, and the sun is completely blocked by the moon. You can actually even photograph and see the stars around the sun during the daytime. And people did that in 1919 to confirm some of the most radical theory back then set by Albert Einstein. We'll come to that later. But so, the sun, similar to stars, sun also changes its position in the day sky. If you go out in maybe in a lakeside or big ocean side, and you can sit there all day, you'd see sunrise at one point in the east, and it will follow through one path and set in the west for that day. Okay. And when the civilization started, when the ancient astronomers, they started to notice something different. The sun does not rise at the same point in the horizon every day. As a matter of fact, that position changes by about 1 degree every day. And so the sun would is, next day's the starting point of the sunrise would move, if to the left or to the right, and even the path of the sun would be different the next day, and it's different the next day. So going from shortest day in December 21 to longest day in June 21, the path of the sun would be different, or the time, the daylight time would be different, because the sun would spend more time between two horizons. That during the longest day, it will cover the maximum path, and so it stays longer during that time. So sun, instead of in winter time, sun sets around 5:30, and you go in the summertime, the longer days, sun is still in the sky till 8:45 p.m. I'm talking about the Texas Arlington days. And so, and that's what the sunrise and sunset is. And how that's happening is, again, when the earth rotates. As the earth rotates, it carries the sun above the horizon, and down the horizon during the set time. And that's today's picture. That's how we know now. But even initially, the facts are there. Science is still the same. The only thing we consider in the past is like how the celestial sphere, all the stars are embedded there, and that celestial sphere would rotate, rise and set. It's same thing. So in the daytime, there's just one star, which is the sun, and sun is embedded in this celestial sphere, and that celestial sphere would move. Okay, the effect is same. Either it's like sun going around the earth, or the earth going around the sun, and that effect would create that sun's position in the sky to change every day, and that thought, or that process, like sun, starting at, let's say sunrise is at this point here, one day, next day it rises here, and that position shift, and after 6 months it starts to go back, and after 12 months, end of 12 months, the sun gets to the same position to rise and set. So there is a cycle. And so this observation, that's when the first observational astronomy was born. These type of observation gave those ancient astronomers the idea that the sun is actually moving around the earth. I mean, now we know it's the opposite, but that gave them that idea that the object must be moving around the Earth, and it's taking some time to go around, and now we call that period of time as 1 year, and it would take 1 year for the sun to go around and make a full circle, and that now we define that as 1 year, but the only difference is the time it takes for the Earth to go around the sun. We define that as 1 year, or 365.2422 days. Okay, I'll stop here. We will go into more detailed geometry next time.